last but not the least group of p block, that is the noble gases. In this, their melting and boiling point are very less because only one type of forces exists, that is the dispersive force, and their electron gain enthalpy and ionization enthalpy are very high. Radon and manganese. Radon is the rarest. Xenon and radon are the rarest metal, and radon and manganese, we prepare radon from the disintegration. Radon break by the disintegration of we prepare radon by the we get radon by the disintegration of radium, atomic number 88, 226 mass. It break into 86 into 222, that is the radon, and emit one helium atom. Then we get manganese from the when californium collide with calcium. Then we get manganese, atomic number 118, 118 and mass 294. And the half-life of organism is 0.7 millisecond. So many predictions about its chemistry have been made because we wasn't actually able to study this, because life, as you have seen, that half-life time is so small. Then electronic configuration, that except helium, everyone's electronic outer shell is filled, that is ns2 np6. Only helium has n1s2. Ionization enthalpy very high because they are stable. Electron gain enthalpy very high. Atomic radii decrease, increase, downside. Very low melting and boiling point, and helium has the lowest boiling point of any known substance. In periodic table, the lowest boiling point is of helium. Then it has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass, plastics. They are least reactive. Earlier, it was not known that noble gases react, but Neil Bartlett in Columbia prepared a red compound which is formulated as O2 positive PtF6 negative. Then he realized that first ionization enthalpy of molecular oxygen, that is 1175 kg per mole, was almost identical with that of the xenon, that is 1170 kg per mole. Then he prepared Xe positive PtF6 negative. By mixing PtF6 platinum hexafluoride with the xenon. Then after this discovery, a number of xenon compound, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. Compound krypton are fewer, only the difluoride of krypton has been studied. Compound of radon not been isolated. 1% normal gases are found except radon and organization because both are radioactive. Then xenon fluoride compounds. How can we prepare? When xenon react with excess of fluorine, we get xenon difluoride. When xenon and fluoride react 1:5 ratio, we get XeF4. XeF2 linear structure, sp3d hybridization. Then when it reacts with excess of in 1:5 ratio, get XeF4, that is hybridization sp3d, and the structure is square planar. When it react in the ratio 1:20, then we get the XeF6 hybridization sp3d3, and distorted octahedral structure is there. All the fluorides of xenon are solid, colorless, crystalline, solid, sublime, readily at 298 Kelvin. They are powerful fluorinating agent, readily hydrolyze even with trace of water. XeF6 can also be prepared by, we can also prepare XeF6 by the, when xenon tetrafluoride react with O2 F2, then we get XeF6 and one molecule of oxygen we get. That is, again we can also prepare xenon hexafluoride by the reaction of xenon tetrafluoride with O2 F2, and we get one molecule of oxygen and one molecule of xenon hexafluoride. Then product of hydrolysis, when xenon difluoride react with water, we get xenon HF and oxygen molecule, and we can draw the structure by the VSPA as we have seen. Then when xenon oxygen compound hydrolysis, when we do hydrolysis of xenon tetrafluoride, we get xenon HF oxygen with XeO3. When we do hydrolysis of xenon hexafluoride, we get XeO3 HF. Hydrolysis of both, complete hydrolysis of both xenon tetrafluoride and xenon hexafluoride give us XeO3, and in hexafluoride only HF is the byproduct. Then if we do the partial hydrolysis of hexafluoride, xenon hexafluoride, then if xenon hexafluoride react with one molecule of water, 1 mole of water, then we get XeOF4, and its hybridization is sp3d2. Hybridization is sp3d2, means octahedral. Let's see, sp3, and XeO3 is tetrahedral, pyramidal shape. Pyramidal is there. XeO3 pyramidal, sp3 hybridized. Then XeOF4, when xenon hexafluoride react with 1 mole of water, then we get XeOF4 and 2 moles of HF, and sp3d2 square pyramidal. It's the structure of and hybridization sp3d2, and when it reacts with 2 mole of water, we get XeO2 F2 HF. XeO2 F2, and its hybridization will be sp3d, and it will be seesaw shaped. Then xenon XeO3 is colorless crystalline, and its structure is sp3 hybridized, and it is pyramidal structure is there. Explosive solid XeO3 is pyramidal molecular structure. XeOF4, when we got XeOF4 when hexone tetrafluoride react, XeOF4 when hexafluoride react with 1 mole of water, volatile liquid XeOF4. Then uses helium is a non-inflammable and light gas, can't inflame, light gas, hence it's used in filling balloon for meteorological observations. It is also used in gas cooled nuclear reactors. Liquid helium find use as cryogenic agent for carrying out various experiments at low temperature. It is used to produce and sustain powerful superconducting magnets, which form an essential part of modern NMR spectrometers. and magnetic resonance imaging system for clinical diagnosis. It is used as dilute for oxygen in modern dividing apparatus because of its low solubility in blood. Neon is used in use of neon. Till now we have seen hitherto that we have seen the uses of helium, then neon used in the discharge tube, fluorescent bulb for advertising display purposes. Neon bulb are used in botanical garden and in greenhouses. Argon is used mainly to provide an inert atmosphere in high temperature and to metallurgical processes, arc welding or of metal or alloys, and for filling electric bulbs. It is also used in laboratory for handling substances that are air sensitive. There is no significant use of xenon and krypton. They are used in light bulb designed for special purposes. So these points were about the Nobel gases 18th group. That's all. Thanks for watching.